Good afternoon, everyone. I welcome you all to week 11 live problem solving session for analog electronic circuits course. And in today's session, we'll be talking about phase margin and gain bandwidth product, etc. So, to understand these, first let's understand the concept of stability because all these things are related to stability. So, what do we understand by stability? So the first question is, what is stability? So, if we talk about a system or a circuit, which has certain input and it gives the output, then the idea of stability is that if we have bounded input, gives bounded output, then system is stable. Now, what do we mean by bounded input and bounded output? So let's say we have a step input. So its value is, let's say, A, amplitude is A, and this is a step input. So what do I mean by bounded output? So it can have different types of output, right? One type of output is, so let's see what are the different possibilities that we have. Yes. So for these four cases, let's check what are the different possibilities for output, okay? Yeah. So if this is the type of input that we have, then what are the possible outputs that we can see? So first type of output that we can see is it will slowly rise and attain the value of input. This is one type of output. It will slowly rise and merge into the input. So this is output. This is one type of output. Another type of output what you can see is, let's say here it is slowly rising to attain the input. Then what happens, rather than attaining the input, it starts oscillating across this input value. This is another type of output that we can have. What else is possible? So your output slowly rises and then it starts oscillating, but slowly it degrades, and at infinity it will attain your input. This is another possibility that we have. So it considers this type of curve. And what else is possible? So your output will be slowly rising, and what happens, it will oscillate across the input, but it will start getting amplified. This is another type of output which is possible for a system. These are the basic four types of outputs that are possible for a step input for a given system. So this type of input output characteristics, where finally input settles, your output settles with the input value, we call it a stable system. Whereas the system where your output does not settle to a particular value but it continuously oscillates across your input value, we call it a marginally stable system. Now, in this third case, your your input is a constant value, but your output is oscillating, but it's a damped oscillation, and at infinite amount of time, or at quite a higher amount of time, what will happen? Your output will settle to input's value, and since there is a possibility that your output will settle at input value, so this is also a stable system. But in this fourth case, what happens is basically your output is unable to settle at your input value, rather, it's getting amplified. And if we continue this oscillation and if we check at infinite amount of time, we'll observe that your output will actually blow to infinite. At that point of time, the system becomes unstable. So, this is an unstable system. So, from these characteristics, we can observe that when you are able to attain a constant output or a stable output, that is where we call it a stable system. And when you are unable to get a constant value or a stable output, that system is known as unstable system. So this is the basic idea of stability. Now, talking about uh, the transfer functions that we generally observe in nature, so majorly we see a two-pole system and and around us, or even when we go for like multi-stage amplifiers and all, we see at least two poles, right? So the basic system that we can observe is a two-pole system. So for a two-pole system, so if there are two poles, then these two poles can have different these two poles can be placed at different locations, right? So there is a possibility that both the poles are, let's say, both the poles are at same location. Both the poles are uh, real, and they are in the negative side of your S plane, or towards negative sigma, and they are at same location. This is one possibility. Another possibility can be like these two poles can be um, like a conjugate pair poles, where they have some sigma and plus minus j omega. So this is sigma plus minus j omega condition. Here they don't have any j omega component. These are real poles. And the third condition, the third extreme condition can be like these two poles are at your y-axis only. Yes. Now, this is another condition where your poles will only have imaginary component, which is plus j omega 1 and minus j omega 1. This is another possibility. So, acha, can you let me know why are we only considering left side of the S plane and we are not going or not talking about the right side of the plane? So, I consider two poles, right? Two poles could have been spread all over. So this is a S plane or sigma j omega plane, whatever it is, the same thing. So these two poles can be spread across the whole S plane, right? But why am I only considering the left hand side of the plane and not considering the right hand side of the plane? What is the reason behind that? Yes? Okay, so I'll answer. What basically happens is when you have a right hand side pole, RHS pole, it gives this unstable behavior. So, this unstable behavior that we have observed earlier, this unstable behavior is due to RHS poles. And we never want an unstable system. So, that's why we never talk about the right hand side poles. Now, there are other three conditions, right? 1, 2, and 3. So, which condition suits which type of pole pattern is the next question. These three systems are stable, right? This one is marginally stable, these two are completely stable systems. So, when we talk about marginally stable systems, so here we can observe that our output is continuously oscillating across a constant mean position. And when these oscillations are continuous and their amplitudes are constant, that means they don't have any real part in them. So, sinusoid, when we talk about a sinusoid, it oscillates across a mean position, right? And its amplitude never changes. So, that means this behavior corresponds to a sinusoid. And when we talk about sinusoid, its roots are j omega, that is only real part. So these two poles, which are imaginary part. So this behavior of marginal stability is present when your two poles are on the imaginary axis, on your imaginary axis of sigma j plane or S plane. So this corresponds to, oh, is my presentation not visible to you? Because it is visible to me. Were you not able to see anything till now? Maybe you can unmute yourself and talk, it's fine. Uh, do you want me to reshare the screen again? Wait, I'll do that. Because I am able to see this, but I'll reshare it. So maybe, yes. Is it visible now? Is my screen visible to you now? Is my screen visible to you? No? Uh, Actually, it is visible to me. I guess there is some issue from your side. Can you do one thing? Can you quickly log off and again rejoin the meeting? I'll wait for you. I'll not proceed further. Can you quickly log out and rejoin again? Okay. Quickly come back. NS, are you there? Hello? 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 Am I audible? Okay, maybe you can go through the recording because I guess there is some network issue from your side. So, yeah, we'll continue. So, talking about marginally stable systems, so when we have poles at the imaginary axis of our S-plane at that point of time, we see a marginally stable system. Now, the second type of system is this is known as a damped system. Here we can see that the oscillations are getting damped and they are slowly converging and coming to a stable situation. So, this is the condition when we have complex conjugate poles. So, okay, so you are unable to log out, that is what you are saying. Do you want me to make you out of the call and you join again? I can do that. Because when you are giving time, so I feel it's good if you can go through along with me because it makes no sense, right? When you are unable to see the screen. Welcome. So I'll do one thing. I'll remove you from the call and you rejoin quickly. Okay? I'll wait for you few minutes, 5-10 minutes. It's fine. I'll wait for you 2-3 minutes, and we can proceed further also beyond time. I don't have any issues. Okay? So I'll do one thing. I'll remove you from the call. You quickly join again. Yes. So this marginally stable system, that is system 2, this corresponds to system 2, whereas these complex conjugate poles correspond to system 3. And lastly, we have a highly damped system, which is the most stable system. It is system 1. And if we talk about the stability, stability also works in this order. So this is the most stable, this is marginally stable, and this stable is this system is moderately stable. Okay. So these are the three types of two-pole system, majorly that we can observe, and after that we can have poles in between this range, right? So these are the two extremes that we have. That is, it can be, it can have two real poles or two imaginary poles. Other than that, it can span in any region of your left hand side of the S plane. So now, when we talk about the values of the poles, for what condition, what type of poles we'll have. So, uh, the first condition is when we have our um, yes. So when we have a system with input and output, like we normally have in our analog circuits, we always know that a feedback always provides a better stability to a system, right? And this feedback is generally a negative feedback because negative feedback provides stability. So if we have a open loop gain of A and feedback gain of beta, then closed loop gain is A times 1 plus A beta. For worst case, we have beta equals 1. So when this is the case, at that time our closed loop gain will become A1 plus A. So now in case of two-pole system, so let's say open loop gain A naught, I'll write it as A naught. So for open loop two-pole system, our open loop gain becomes DC gain by 1 plus S omega P1, 1 plus S omega P2. So its closed loop gain will become A naught upon 1 plus A naught. So this turns out to be A naught omega P1 omega P2 by S square plus omega P1 omega P2 S plus omega P1 omega P2 A naught plus 1 Since a naught is much greater, so we can simply write it as ADC होगा ना. This is ADC. These are all ADC. ADC omega p1 omega p2 upon s square plus omega p1 omega p2 of s plus omega p1 omega p2 into ADC. So yes. So when we have a tuple system, we know its general transfer function turns out to be omega n square upon s square plus 2 alpha omega n s plus omega n square. So from here, omega n turns out to be root over omega p1 omega p2. 2 alpha omega n is omega p1 plus omega p2. So 2 alpha turns out to be omega p1 plus omega p2 by root over omega p1 omega p2, where this 2 alpha is actually a damping factor. Yes, so omega n is omega p1 omega p2 into ADC, and 2 alpha is this expression. Now there can be different types of situations, right? So first case is I'll change the color here. So case 1 is when omega p1 equal to omega p2 is equal to omega p. So that is both poles at same frequency. So in this case what happens, our omega n will become root over ADC omega p, and 2 alpha will become 1 by root ADC to, so alpha will become 1 by root over DC gain. This is what that will get, and if we closely observe, ADC is very high value, so alpha almost becomes equal to 0. So H's, that is closed loop transfer function, will become omega n square upon s square plus omega p square. So ADC p square. So this will give us 2 imaginary roots. So when we have 2 imaginary roots, that means it is a marginally stable system. So it will have a behavior like, for an input of step function, we'll have a oscillating output, and the system will be a marginally stable system. This is case 1. Now next comes case 2, that is when we have open loop poles, that is two open loop poles with one being much greater than the other. In that case, let's say omega p2 is 4 times of a naught omega p1. In this particular situation, what happens? Alpha is so this closely becomes equal to 1, as this almost tends to 0, and 4 in ADC, this is DC, is much greater than 2. So alpha becomes almost equal to 1. In this case, HS will become omega n square upon s square plus 2 omega n s plus omega n square. So when this is the condition, we'll see a stable system say a stable system which is like, so if this is the input, so the output will be a damped system. Now this is the situation when alpha is almost equal to 1, but for alpha much greater than 1, let's say, or alpha greater than 1, then what we'll observe is the system will slowly convert into this, so there won't be any oscillations. This is for alpha greater than 1. This is the condition for alpha almost equal to 1. So these are the possible conditions along with the poles. Now when we talk about phase margin, so what happens? It is minus 180 degrees plus phase of the system. So more the phase margin, implies more stability. This is the basic idea that we have. And as it already has been mentioned in the lecture, that is, the phase margin is calculated at the point where, so let's say this is your gain frequency plot, and here you have phase and frequency plot. It always starts from minus 180, right? So, or when we have a phase, and let's say you it starts from 0 degrees. It depends what is the phase that it is starting from. Let's say this is your phase plot. So you basically have to see, like, at your unity gain frequency, what is the phase phi, and your phase margin becomes minus 180 plus phi. This is the phase margin. So now talking about phases and phase margins, and we already talked about how poles should be separated, so here, as we have observed, that when two poles we have, and those two poles are overlapping each other, we get a marginally stable system. Whereas when these two poles are far apart, we get a stable system. This is stable, right? Stable system. And as we increase them much higher, so here we had 4 ADC, the difference between like ratio of omega p1 and omega p2 and omega p1. When we further increase these, our alpha also increases, which basically increases the damping, and we get even better stability. So the key point to be noted is, farther the poles, or more separated the poles, higher implies higher stability. This is something that we need to keep in mind. That is, more separated the poles, the higher we'll see the stability. Now, why do we need to consider this, right? This question basically comes into mind. So let's look into this first question. So here we have the circuit, right? In this circuit, these both the transistors are in MOSFETs, and here we have drain node, source, gate, drain, source, gate. We already know that drain node has higher R, right? And also, if we consider these capacitor values, they also have higher C. So if we observe carefully, the value of R1C1, um, let me like, yes, so R1C1 is almost very close to R2C2. So this implies that there is a possibility that our system tends towards instability, or we can say marginal stability. So that's why it is necessary for us to have R1 C1 R2 C2 upon R1 C1 much at least greater than 1 or much greater than 1, so it's very good. So ideally this is the idea. So how can we do this? Now one thing that we can consider is actually at these 2 points the capacitances are not equal. That is because of this Miller capacitance. So this will come here as gain times of C12 or 1 minus gain times C12, whereas here it will appear as simple C12, right? Very close to C12. So here we can definitely see that the capacitances are not equal at these 2 points. But is there a way through which we can further separate these two poles? So see, at these 2 points, the resistances that we observe at these 2 points are very important. Why? Because the gain of this whole system becomes GM1 R1, GM2 R2. So if we try to reduce the resistances or play with the resistances, our gain will be affected. So what else we can do? We can play with the capacitances in this region. So to make these poles far apart, we can again add another capacitance. We call it a compensation capacitance. So these capacitance will again show that similar Miller effect. So what will happen is this will again appear here as 1 minus A times of Cc plus C12, and here it will appear as almost close to 1 times. So I'm writing C1 plus Cc plus C12. Okay. Now this capacitance is something which will have external access to. So you can basically control this capacitance. This is known as compensation capacitance. We have access to this capacitance. We can simply uh, tune this capacitance and we can adjust the values for these poles at these two nodes so that our poles are far apart from one another. So this is what is related to compensation capacitance. Now coming back to this particular question. So in this question what has been asked? So the question is that consider there are two stage cascode amplifier this is. Here all the values have been given like GM1, GM2 and lumped resistances and lumped capacitances have been given. Now here phase margin has been given. Excuse me, I guess your mic is unmute. Can you mute yourself? Raghavendra sir, can you mute yourself? Okay, so here it's given that we need to have a phase margin of 75 degrees. Now it is asked that what should be the ratio of two poles of the circuit. So we need to find out the ratio of two poles. Okay, so the ratio of two poles is given by, so the ratio of two poles was called as x, and this was also derived in the lectures also. So the formula for x which was derived in class, that is ratio of two poles, is a naught square minus 1 upon 1 plus a naught cos phi minus 1 plus a naught cos phi. What is a naught? A naught is the DC gain, and a naught is given by gm1, gm2, r1, r2, and phi is phase margin. So when phi has been given and we know the values for gm1, gm2, r1 and r2, then simply we have to substitute all these values over here and we have to find this x. And when we find x, it turns out to be 810.98. The ratio between two poles is 810.98 for the phase margin of 75 degrees. So this is the first question that we have to solve, and this formula was there in last week's lecture. Maybe you can look into it to revise again. Now coming back to the next question, which is basically a follow-up question. So in this question, the idea is to design a compensated phase margin of 75 degrees by adding an extra capacitor of Cc in shunt with C12. So shunt means parallel. So we have to, in parallel to C12, we have to add another capacitance which is Cc, such that we get a phase margin of 75 degrees. So what is this value of Cc? That is the question, and we have to answer in femtofarads. So for this question, we know that the transfer function contains two poles and one RHP 0, right hand plane 0, from the short circuit currents. Now when we work on it, when we want to find out the two poles, for that we need to know the output impedance, and the output impedance is given by R2 1 plus S C1 R1 plus C1 to R. It's a big expression. You can solve this. Is R1 C12 plus R2 C2 plus R1 C1 plus R2 C12 plus GM2 R1 R2 C12 plus S square C1 C2 plus C1 C12 plus C2 C12 into R1 R2. Now when we assume two poles are far apart, then 1 plus S tau 1, 1 plus S tau 2. So the tau 1 and tau 2 are 1 by RC, right? So poles, 1 by pole, that is the basic idea, is almost equal to 1 plus S tau 1 plus S square tau 1 tau 2. So we have neglected the other one. So here one time constant will be R1 C12, R2 C2, R1 C1 plus R2 C12 plus GM2 R1 R2 C12. So this is 1 by of the pole, right? 1 by omega p. So it is 1 by omega p, and I'll write it down so to make it simpler. The T2 is tau 2, and this is given by C1 C2 plus C1 C12 plus C2 C12 into R1 R2 by tau 1. So the ratio of two poles, that is tau 1 by tau 2, which is basically the ratio of two poles, no? Omega 2 by omega 1. So this is equal to R1 C12 plus R2 C2 plus R1 C1 plus R2 C12 plus GM2 R1 R2 C12 square by C1 C2 plus C1 C12 plus C2 C1 2 into R1 R2. So this is the ratio. Now we also know that x is equal to a naught square minus 1, the formula that we used earlier, 1 plus a naught cos phi minus 1 plus a naught cos phi. So from here, phase margin, that is phi, has been given to be 75 degrees. Since a naught is also known to us, that is gm1, gm2, r1, r2, so from here we'll get the value for x, right? And in all these cases, we need to find out now. Here there is one thing, that is, here we are using C12, right? In all these formulas we have not used CC, we have only used C12. So what we can do from this x and substituting all other values, and so from expression 1 and 2, if we equate, so we'll get x equal to some expression as a function of C12. So rather than substituting C12, we'll substitute all other variables, that is R1, R2, GM1, GM2, okay, R1, R2, GM1, GM2, C1, C2. We'll substitute all the values and we'll make C12 as a variable, and we'll solve an equation. So we'll get a quadratic equation with variable C12. Okay, now when we now we'll get a quadratic equation in terms of C12. So we have to solve the equation, and we'll get it like plus minus b, minus b plus minus root over b square minus 4ac by 2a, as we simply solve the quadratic equation. So we'll get the values for the capacitance, and one value So in this we'll get two values for C12. One value will be minus 2.288, whereas other value is minus 1.38. No, so here uh, rather than this, I'll let you know the values for these small a, b, c. What are the small a, small b, small c that we'll get? So a we will get to be 6 to 5 4 8 7 8 8 4 3 4 3.53. Yes. So this is the small a that we will get. Small b will get to be minus 2.28809, and c we will get to be minus 1.3834 into 10 to the power minus 12. With these three values, we'll get the values for C12, and definitely there will be two values because of this plus and minus. Now we need to see what is the closest and most possible value that we have. So finally, when we arrive and find the value of C12 from this expression, now what we have to do is, we already know the C12 given in question is, so I'll write it as C12 dash given in question. So when we get the C12 from here, so this is basically Cc plus C12 dash. So to find the compensation capacitance, what we'll do, we'll take the value which we are getting from above, we'll subtract it from the value given in the question. So we'll finally get the compensation capacitance, and this turns out to be, compensation capacitance turns out to be 4166.398 femtofarad. This is the value that we'll get for the compensation capacitance. Clear? Now, next thing is, for suppose rather than compensating it with so what happens is, when we have this C12, so the CC and C12, they will lead to right hand side plane 0, and there are chances that this 0 comes uh, in it comes before, I would say it comes before uh, dominant pole. Let's say there are chances that this 0 may come before the dominant pole. So if this happens, then what will happen? It will disturb the frequency response completely. See, response completely. So what happens when this is the case? Then what we want, key, the 0 that appears, that is RHP 0, should have frequency much higher than dominant pole. If that is the case, then it will not disturb our system. So for that, uh, as you might have observed in the lectures of this week, so sir discussed this idea, and he also told us like how to find out the value of this RHP0, how to calculate the value of this RHP0. There he also mentioned what will happen if in place of this CC, if we have a CC as well as RC, CC dash and RC dash. If this is the condition, then how the things will change. So maybe you can look into it in the lecture. I'll directly go ahead and solve the I'll go ahead and solve the expression. So the expression for RHP pole, RHP 0 turns out to be Gm by Cc dash upon 1 minus Gm Rc dash. So this is the formula when we have both Rc dash and Cc dash in circuit. So when this happens, now what we want that the frequency of our RHP0 should be much higher, and if it becomes infinity, then it's well and good. So for the case of when RHP0 is equal to infinity, 1 minus Gm Rc dash should be, and this is, mind you, this is Gm2 is equal to 0. So this makes Rc dash equal to 1 upon Gm2. So this is the final answer. Here Gm2 was already given. So Gm2 was how much? Gm2 was Gm2 is 1028 microsiemens. So since Gm2 is 1028 microsiemens, 1 by Gm2 turns out to be 972.762 ohms. So this is the compensation resistance that is applied in series with the capacitance to move 0 far away from the dominant pole. Yeah. So these were the three questions which were connected with this first question itself. So this was the circuit which has been used throughout. So in first question it was the simple circuit, and second question, the next question what we did. So this is question number 2. This is question number 1. So and this is question number 3. So this is question number 3. So in first question that we solved today, what we did was we solved the simple circuit which was given for a given phase margin, and we found out the ratio between the two poles. In the next question, what we did, we added a shunt capacitance, which is a compensation capacitance, and we again solved the question for 75 degrees phase margin. Now the next question was regarding the right hand plane 0 that appears because of this compensation capacitance. So how to mitigate this problem? So for this we'll use a series resistance in series with the shunt compensation capacitance so as to move the 0 far away from the dominant pole so that it does not affect our frequency response. So for that we solved this problem and we got that our shunt resistance value actually turns out to be 1 by GM2. So these are the problems that we discussed today, and before this we discussed about we have given quite some time for the concepts on stability and why stability is important, what is the basic idea behind stability, what we understand about stability, and all this. So hope this helps you solve the problems for this particular week, and if you have any particular questions, feel free to ask. It's already 4:12, so maybe we can stop the session if you don't have any further questions. Any doubts? Any questions? No doubts? Okay, since you people don't have any doubt, so hope whatever we discussed today is clear to everyone. So that's all for today. Thank you. Have a wonderful evening ahead.